Hello and welcome. This is Dr. Hisham Saeed. Welcome to this video. It's the last part of the first lesson of strength of materials, where we will learn about bearing stresses and the use of factor of safety in analyzing strength of materials. So the first question is, what is bearing stress? So bearing stress is the compressive stress that's acting on in the contact area between two members. One of them is carrying or supporting the other one. So it looks and feels like a normal stress. So we even analyze it or refer to it using sigma notation here, but we just differentiate it with B. So sigma bearing here is equal to the force over the area or the contact surface area here. It's not bearing stress is not, or bearing failure here is not that significant compared to normal stress failure. Normal stress failure will cause a complete failure in the member, like breaking it or compressing it, buckling. But bearing will cause local crushing failure. So that will over time cause deterioration of the members and will cause misalignments and different things, but it will not cause the failure of the whole structure. It's more local, and it will look like you're crushing one member by the load applied from another member. So that's one difference between bearing and normal, that this kind of local versus global failure of a structure. Another thing is bearing is between two members. The stress is developing between two members, but normal stress is a stress developing within a member. So we'll see a couple of practical examples of bearing stress. The famous one is in bridge design and construction. So in this photo here, this is a beam of a bridge that's carried by a pier of the bridge here. And when we design this beam, we design it as a roller connection here. So we allow the beam to roll, but we cannot make it roll on these two hard surfaces. So we put pads, elastomeric pads here, special material that kind of will absorb that load and allow that sliding of the member. Over time, these pads deteriorate and get crushed by the beam loads. So that's one example of bearing failure here. Another example is happens in connections, bolt connections. So these two bars here are kind of welded to plates, and these plates are connected by a bolt. So we see here that little, crushing here of the metal that's being crushed by the bolt. So that's the bearing failure. If we see here that some bearing happened here and here, but it didn't cause the failure of the connection. What caused it is actually a tensile failure. So we'll see that in the next lessons. There is necking here happening, so that's a clear indication of tensile failure. So connections give a very interesting example of tensile failure, of kind of examples of, and good examples of combination of different types of failures. So in this connection here, a typical bolted connection will have 5 possible failures here, like we'll see. For here, I have 5 possible failures. I'll give you maybe a moment to think about what possible failures can happen in this connection. And the connection is made off of 2 plates that are connected by a bolt or a pin. And they are 5. So let's see now these 5 possible failure scenarios. So the first one here is the tensile failure in the top plate. So there is the force is flowing through the top plate, and the cross section of the top plate is W cross A. So the stress that, if we're not designing it carefully, that stress sigma will cause a failure in this plate. A second failure scenario would be the lower plate, or the bottom plate. Now, because we have different cross-sectional dimensions, we have a different sigma here. The third failure would be the shearing of the bolt. So that shearing here in between these two surfaces across the bolt is a third possible failure that can happen in this connection, and it's tau. It's the shear stress, P over area of the bolt, and if we say the diameter of the bolt is D, then we can calculate the circular area of the bolt. The fourth possible failure is the bearing failure in the top plate and the bearing failure of the bottom plate. And what we do here is, if we look here, the contact area between the bolt and the plates is kind of a half surface, external surface of that cylinder shape. But we do rough approximation here. We only consider the projection of that curved surface, and projection for the top plate here will be A times D, and for the lower plate will be B times D. So we see here connections kind of give us interesting example of different failure scenarios, and every one exhibits possible failure from possible stresses exceeding their limits. So now, when we're aware of now these type of failures, next question comes, which is, should we design members to allow them to reach the ultimate capacity? So if you remember from Mech 15, or the course we learned about materials, you learn about there is an ultimate stress, where or ultimate load. So that member or that material cannot take more than this. So the question is, should we design for this material to reach the ultimate in the field in that structure? Question is, by practice, no. We actually design that when we do the calculations, the ultimate is not our goal. We actually set our limit lower than the ultimate, which we call allowable stress. And there are many, many reasons for that. So the first one is materials are not homogeneous, mostly in most cases. Metals, yes, like steel, aluminum, there's some high certainty about the performance in different samples, but still there are variations. It's a completely different wild kind of case in non-homogeneous materials like concrete. So we cannot assume with certainty that the ultimate stress will be the case for all cases of loading. Another reason is there are different cases of loading. So there is wind, earthquake, dynamic, static. So there are different loading cases. We try to come up with all critical possible loading cases, but in the open environment, we don't know what will happen in the future. So the third one is the quality of installation and manufacturing. We don't know what quality standards will be enforced, so we try to account for that. Many, many reasons, like the accuracy of estimating the loads can be questionable. So factor of safety is used to account for all of that. Factor of safety is basically the ratio between the ultimate stress that we kind of figure out from experimenting with the material in the lab and the allowable stress that I will design based on it. So it's either the factor is the ratio between either the ultimate stress or allowable stress, or the ultimate force and allowable force. But we usually deal with the stresses because this is where we can get from the lab and also what we can get from our calculations, and it is the normalized way of dealing with forces. So factor of safety Fs here is equal to sigma ultimate over sigma allowable. We're just giving an example here of normal stress, but it can also be tau ultimate over tau allow, right? Or sigma bearing ultimate over sigma bearing allow. So the bottom line here is sigma allow that we use to design or allow a member in a structure to reach is a reduced value of the ultimate stress of that material by a factor of safety. And factor of safeties can go from all the way from a value above 1 all the way sometimes to 5. It depends on the material, depends on it depends on what code requirements are enforced in that case of structure and what application it's used for. So sigma ultimate is identified from lab tests, like you will see in the lab sessions of this course, and factor of safety is suggested and enforced by design codes that we use in civil engineering, mechanical engineering, different fields of engineering. And now when I start designing, I calculate sigma max, that maximal observable or possible stress that can come out of the load cases I'm analyzing, and I want this sigma max to be less than sigma allow, and I'm considering sigma allow to be less than my ultimate sigma by a factor of safety. So factor of safety is very important. I cannot design a material to reach its ultimate stress in the field. I have to design it considering that it will reach only an allowable limit of this. Another reason I did mention about the factor of safety is we are designing assuming that everything is linear. So that's not the case. If you go to the lab and you'll see the stress strain diagram of materials, there is one little tiny part of it is linear and everything else is non-linear. So we use factor of safety to bring from the ultimate stress down to the allowable stress that we want to be in that linear phase or region, because all our assumptions are based on linear modeling. So that's another very important reason why factor of safety is used in strength of materials or analyzing the capacity of materials and designing members and connections. So we'll see here now this example to combine that idea of calculating stresses, comparing it to ultimate, but not really the ultimate, considering the factor of safety. So we're calculating here allowable stress and comparing it to the possible maximum stress that can happen in this loading case. So we have here this wood block that's kind of resting on the ground. That's not mentioned here, but that's just kind of one thing important to notice. So it's resting on the ground and there's a steel bar kind of pushing down, and this is why we're giving you two ultimate stresses. One is the ultimate stress of the bearing, ultimate stress of the bearing of the wood, and then the ultimate stress, shear stress of the steel. So that gives you a hint of what type of failure cases we're trying to analyze here. And we're trying to figure out what's Pmax that will not cause, that we should allow that structure to breach, considering that we are enforcing here a factor of safety of 3.2. Once you do that, we'll see what change will happen if we flip that system, and that wood now is not resting on the ground, it's up to the air. We're pulling the bar up. So now we're concerned about the ultimate shear stress of the wood, and we'll see what type of failure and how the look and the shape of that failure of shearing through the wood. With this change value of Pmax, this will be kind of a second type or a second phase of this problem. So here like we mentioned, the first part of the problem, we're given two ultimate stresses. These will give us a hint on what type of failure scenarios will happen. So we're thinking about two possible failure scenarios. The first one is the shearing failure in the steel rod. recognize that always we design based on the allowable stress, which is tau ultimate divided by factor of safety. In this case, it's a shear tau. I'm considering here the values given to me, so this means that the allowable shear stress for the steel is 45.3 megapascal. Now I will design, trying to figure out what would be the maximum tau that's created by this load P, and make sure it doesn't exceed tau allow. Now, like we said, we make an assumption that tau here from a shear force is equal to this shear over the area. Disclaimer, we will say that we are actually revisiting that in the future to calculate tau in a different way, more accurate way. So V here for, and what type of shearing stress happening here? It's double shear, right? We have here P is split on both sides of the member, and there is one P coming from the wood applied on the bar. So kind of we see two shearing actions happen on both sides of the bar here. We're analyzing one of them, and this is why we have half of the force applied here, P over 2. That's my shear stress, shear force. So shear stress is equal to V over A. V is half P max. Now this is kind of giving a max notation here, subscript. And my area here is the area of that circular bar. And if I solve for P max, I'll find that it should be less than or equal to 10.25 kilonewton. The second failure mechanism here I'm analyzing is the wood bearing failure. So that bar with the load will crush the wood contact surface with it on the bottom. Drawing it here as this half circular surface, but I'm making an approximation here to be the projection of that surface. So it's the width of it is the diameter of the bar, and the length of it is that length of the block, 40 millimeters. So sigma allow bearing is equal to sigma ultimate bearing over the factor of safety, and that will give me 4.3 megapascal. And my goal is to allow sigma max to be less than or equal to sigma allow. For sigma bearing, it's equal to P max, because the P over 2 add up together and compress that area together. So P max divided by the area, 0.04 millimeters times 0.012 millimeters. And this should be less than my allowable stress. And if I calculate P max, it should be less than 2.07. And this is my second condition for P max. Now, which my ultimate, my limit here for P max, considering these two limits, I should pick the minimum one, because if I pick the largest one, then the second condition will not be satisfied, and the system will fail under bearing here of the wood. So here, my P max would be the least of the two conditions. P max is less than or equal to 2.07 kilonewton. Now this is the first case. Now the second case, so if I flip the system, now I'm analyzing, or I'm giving here the ultimate shearing stress of the wood. So now I have one more possible failure scenario, which is shearing of the wood on top of this bar. And if I draw that, kind of showing here that if it fails, I will just punch through the wood with this kind of block on top of it. And these are the dimensions. Now, what type of resistance that is trying to prevent this failure from happening? It's the shear stress on the surface of the wood that I see here, but it's not only one surface, it's actually both sides of that block that tries to punch out because of the bar is pushing up. So now the 2P over 2 is resisted by shear stresses on these two opposite surfaces of the wood block. So going back, trying to figure out really my threshold of design here, which is tau allow, considering tau ultimate wood that's given to me and the factor of safety of 3.2. And I'm now designing that tau max of the wood should be less than tau allow. Tau max here from equilibrium, the shear stresses on both surfaces just before the failure should be equal to 2p over 2. So 2p max over 2 divided by the area that's relevant to these shear stresses developing. So it's 2 surfaces, and each surface is 4.04 meters times the depth of the block, which is 0.055 meters. That should be less than the bearing allowable stress. If I calculate that, I come up with a third limit. Considering the limits I had before, 1 and 2, and this one, I still constrained by the wood bearing failure from the previous case, and still my Pmax should be less than or equal to 2.07 kilonewtons. So that's a very interesting exercise. You see the different possible failure, and we engineers love to design and think in a dark way, kind of. We want to see what failure will happen and counter that to design the system so we don't reach that failure actually. So that's kind of the last thing we covering in this video. Hopefully it was clear and interesting for you, and see you in other future videos. Thank you.